Okay, so welcome to the last session of today. I guess my first announcement is we'll have a change in speaker for Xilinx, and it's my pleasure to introduce Nick Nee from Xilinx. Nick is the Director of Product Marketing for AI software and ecosystem for Xilinx. One of the trends that you've seen in the industry and certainly here at the summit today is the fact that neural network designs are evolving and they're fluid, they're changing, and that's difficult if you want to build an accelerator in an ASIC. So I think Nick's going to tell us about a better alternative to ASICs for accelerating neural networks. So with that, Nick.
All right, thank you so much.
Welcome.
Is that one?
Yep.
Okay. All right, good afternoon, everybody. Thank you so much for sticking around. I understand this is the last presentation, so you guys are still standing strong. Thank you so much. So unfortunately, Vinod Catheo had a personal emergency, so I'm pinch hitting today. But nevertheless, I'll try to do a fine work here. So today we'll talk about the Xilinx AI Engine. And for those of you who follow Xilinx, this is our next generation 7nm device that we announced in last year. And as part of a device announcement, we call it Versal ACAP. There is a very new component called AI Engine, which is going to be the focus of today's presentation. So before we begin, I want to talk about the motivation of AI Engine. And I think the name kind of spills it, but that's basically the motivation, right? AI is everywhere. We are clearly seeing, and I'm sure you've heard plenty of topics today, right? AI is not only hot, not only buzz, but it's finding way into products, commercializations, and monetizations. And some of them are already being deployed. For example, data center, right? Your speech recognition from your phones. Every time you do a search, there's recommendation engines that's showing you what you may be looking for. These are all AIs running in the data center, but also on the edge. Like a lot of the cameras nowadays can do face detection recognitions without people always doing a manual inspections. Both automotive, right? Some of the premium cars today can already do blind spots, emergency braking, and this is heading to much higher autonomy, right? The key is though, although you hear so much buzz, so much great work happening on the AI, the deployment and commercialization is still very limited, right? I mean, how many cars has AI today, right? How many data center? I mean, it's still really getting started. And one of the biggest reasons is hardware, right? Hardware is still limiting the fact, today's AI neural networks are extremely computational intensive. That, if you need to meet everything from performance, latency, power, and even cost for particular application, it is really hard to find a perfect hardware today. And this is really the race for the right hardware for the AIs. But also that requires not only betting on the technology scaling, right? Waiting for the Moore's law, waiting for next gigahertz. It just doesn't happen. We need orders of magnitudes kind of boost in these performance. So what we saw was we had to do something fundamentally different, right? Not only we go for 7nm, which give us much more efficiency on the power, but also significant architecture change in the silicon itself to adapt to these demanding workloads. So with that, we introduced our next generation 7nm Versal ACAP, right? And this is, think of, Xilinx had product lines like SoCs, like Zinc, and also FPGAs like Kintex and Vertex. And this is a new category of device called ACAP. And Versal is the first code name for that. And this is a fundamental change in the architecture. Of course, 7nm is we're one of the very first ones to go to 7nm. But also architecture-wise, you see the scalar engines now, it's going to the A72. So we're basically doubling the performance compared to our 16nm. Adaptable engines, it's basically what we're known for, the programmable logic. And this is getting 2x the density by going to 7nm. And if you look at the actual absolute performance, it's going to 8x compared to 16. So that's a significant amount of leap on the programmable logic. And then there's a complete new block called AI Engine, right? And which is the focus of this talk, so I'll talk more about that. But that is a fundamental leap. DSP engines also are significantly improved. Now we can do 3 max per clock. and also supports floating points, etc. And then in between all these, there's a network on chip. So this allows you to run transports between different blocks in a gigahertz plus range without doing a place and routes. So one, it saves a huge amount of programmable logic and saves the hassle for the time enclosure, right? Now, for IOs, we've hardened a significant amount of IOs like DDRs, HBM, PCIe, C6. And the idea is we wanted to kind of go for this shell and a row model. How many of you heard of this shell and the row kind of concept? Okay, so it's a bit of data center concept, but if you look at it, all the A72R5 and the IOs are already pre-configured, predefined. There's nothing you have to do, right? It just boots up. It's a hardened. Now, it allows you to focus on the adaptable engine, which is your programmable logic, and the AI engine, which we'll talk about more, right? And then also DSP, which everything is software programmable. So this makes it, now the shell brings up with the basic interfaces, and then you really focus on your value add. So the concept of AI engine is, first, it's extremely fast processing units, right? Vector units, which runs over 1 gigahertz. And each of the cores will also have a huge amount of bandwidth around the cores and also in the cores. And we can actually pack up to 400 of these AI engines in a tile. So, significantly multiplying the computational. And from density-wise, it's almost 8x of the compute density compared to 16 nanometer, and the power is going down by 40%. And, there are a lot of different ways to use this, but we primarily designed this for AI inference and also 5G signal processing and some of the computer vision processing. It's really where we see the sweet spots for these AI engines. And then one of the key benefits that we're really trying to bring through this major re-architecture of the silicon is software programmability, right? Now, the world is going to data center, going to the AI, and one thing common about these is software programmability, right? The abstraction of these development environments are going higher and higher, and we're really trying to make the whole chip programmable through software. So, traditional C, C++, now Python, and also we're trying to bring in lots of vendor-optimized libraries, like 4G, 5G libraries, computer vision libraries, and AI libraries. And so for something like AI, we're bringing even higher level of abstraction by going to the industry standard framework. So you can program directly from Caffe, TensorFlow, PyTorch type of frameworks. And then, providing with a familiar software environment so we can compile, debug, and profile. Remember, having lots of those knock and hardened blocks will give you more traceability, more visibility into the system, so you see where the system bottleneck is as well. So that's kind of the major concepts. And now you may ask, with all these major architecture change, what's the benefit? And this is the benefit, right? We're looking at AIs compared to 16 nanometer from Xilinx. For something like GoogleNet, less than 1 millisecond latency, we're seeing 20x kind of boost in the performance. For massive MIMO radio, for 5G use cases, we're seeing 5x. And meanwhile, achieving about 60% of the power. Okay, so now let me kind of deep one level down into the architecture itself. So AI engine is, at the concept level, it's a tile-based architecture, right? So think of it as a big vector processor that you can program through instruction sets. And it has the AI vector extensions as well as 5G vector extensions. So clearly we're targeting these by morphing a little bit of the vector processors. But also it has a local memory in each of these tiles. So you can store enough buffering, do all sorts of orchestration like streaming, broadcast, and the message passing. Now there's also interconnects in between those, so you can actually tile multiple of these together. So each of these AI cores can be connected. And then finally, FPGA is known for streaming, right? We have a cascading interfaces. So, for the neighboring blocks, you can really cascade it as if you're programming the FPGAs. So it has a full flexibility, as you can see. And then once you put this together into array, right? That's what really the AI engine is. We can basically stack up to 400 of these. So different devices will have a different size, number of AI engine configurations. But this really brings the huge multiplying effects on the computation, but also huge amount of flexibility and memory bandwidth between these cores. Now, further zoom into the actual AI engine processing core itself. It has a scalar unit, which can do a 32-bit scalar RISC processing, and also the vector processor, which can go up to 512-bit SIMD. And then again, there's local memory and also streaming interface. So with all these, we can explore two different types of deep parallelism, right? One is SIMD parallelism, where you can have one single instruction, have very wide data, and you compute on those. But also you can do a more heterogeneous processing. We can support up to 7+ operations, heterogeneous instructions clamped together, which is VLIW, right? And that can be done as well. So just to kind of illustrate the flexibility of this thing, right? I don't want you to kind of take away saying this is another ASIC. This is really much higher performance, ASIC class performance, but then with a full flexibility around these AI cores. So you can do the classic ping pong, right? For example, you can have multiple AI cores connected and they use the local memory to ping pong, right, into a pipeline. You can also have a much complex data flow graph where one AI core broadcasts to 3 different memory locations and then it continues to stream. And these are deterministic, right? Remember, all these interconnects are non-blocking and all the memories are locally distributed. So you can really carefully program this so that it becomes a complete streaming pipeline. For non-neighbor AI cores, you can use a memory and there's a DMA built in as well. So you can actually transfer data from non-neighbor AI core to the another AI core as well. We also support multicast and streaming. So at this point, I hope you start thinking like what kind of thing you can be doing with these kind of cores, just like how you design your most efficient FPGA designs. Now, so far I've mostly talked about the AI engine itself at the tile level, at how you put those in the 2D matrix. But what makes it truly unique is how this integrates with the rest of the Versal device, right? AI cores and array of these are already quite flexible, but we actually put this very tightly integrated with the network on chip and the programmable logic itself. And this is really where we feel the major differentiation. Anybody can create ASICs and a huge amount of big leap on the performance, but then how do you keep the balance of flexibility and order of magnitude speed up in the hardware, right? Yeah, we think the answer is programmable logic. That's our sweet spot. By having that with the terabytes of bandwidth between these two, you can, for example, have custom layers running there while most of the convolution is running in the AI engines and still have the memory hierarchies, custom memory hierarchy in the PL to really pump the data fast enough into these AI engines. And honestly, that's really the major challenges in many of the computer architecture today, that you just can't pump the beast fast enough, right? And FPGA, if you think about it, that has been a sweet spot. You can create the custom memory hierarchy to pump the data based on your workloads. So we're trying to strike the right balance between those two by having ASIC level performance AI cores together with programmable logic all together. And then just one more point. You may now be asking, okay, so this looks interesting, but what's the benefits or difference compared to this and the, say, traditional multi-core and many cores? It's really so traditional multi-core is more cache-based architecture. So you're really competing for multiple layers of cache, right? So you may have 3 different cores. Each of them may have a level 0 core cache, and then level 1 is shared, level 2 is further shared. So what happens is core will look for data in L0. Hopefully it's there, but it's not. It's a cache miss, and you go to the L1. There you're competing with other cores. And if it's not there, you go to L2. At this point, I lost my determinism, right? I can't kind of predict when exactly it's going to come back. Also, meanwhile, I'm continuing to replicating my data into a different cache, so you're incurring more bandwidth, etc. Now, if you look at the AI engine arrays, everything's first non-blocking. So each of the cores has its local memories. It has its dedicated interconnects and DMAs, etc. So you can carefully program this so that it never blocks, and it's very deterministic. And also, because of the distributed architecture, we can use much less memory as well. So we don't have to have a huge cache, and hence, much smaller memory in each of the cores, saving the footprint, again, saving the power. So that's where we kind of see the major difference and major benefits compared to traditional multi-cores. And because of all the reasons we said, we're seeing a huge amount of efficiency, again, because of the flexibility, right? So for machine learning convolutions, based on the matrix multiplication, we're seeing up to 95% efficiency, FFT at the 1024 points, 80%, and DPD is 98% unheard of kind of efficiency, right? This is extremely promising for us, and again, combining this with the PL, will give us a lot more flexibility as well. So far, I've been promoting about the hardware portions and the architecture portions, but the real intent is to expand our user base, right? With this, making this software programmable. So by, again, creating most of the IOs and scalar engines to be in a shell, which means predefined, pre-built components, and allowing developers to focus on AI engines, programmable logic, and the DSPs, we can now significantly abstract the programming models. So we continue to have a Vivado design suite, extremely important for our hardware users. And on top of that, we'll be building a unified software development environment, which allow you to develop in the higher languages. But then the key is above that even, right? Many people, especially software developers, expect vendors to provide a lot of optimized libraries and framework supports. So this is exactly what we're going to do, right? For AI is a classic example where we're abstracting all the way up to Caffe, frame, TensorFlow type of levels, and allow you to almost seamlessly target the FPGAs from your Caffe TensorFlow trained models. And at the very high level, we haven't announced this one, so I'm just going to talk at the high level. It's a unified software development environment, allow you to program using C, C++, and Python type of languages. And clearly, the scalar engines are ARM, right? So you can target that through C, C++. Programmable logic, you can use RTL or you can use C, C++ for the high-level synthesis. And the AI engine is C programmable by design. And we'll have a lot more ease of use features, so you can easily write behavioral C code for your VLIW and the SIMD engines. But then the key is, how do we stitch them together, right? There's a lot of data movers, there's a lot of system-level plumbing implications, and that's something we intend to take care of also at the software development environments. And another benefit is system simulation and profiling will get a lot more enhanced. Because of network on chip, we also have a lots of tracing and profiling debuggability built in. So we can actually show much bigger and much more in-depth visibility into what's happening at the system bottleneck level as well. So just a few examples. These are kind of things you could be doing and you could be programming using these kind of models. One is you create your own data flow model, right? Just like how for those of you who have used Xilinx before, you can use APIs to develop something like this. And you can do the similar things by conceptually coming up with function A, B, C, D, E, and these kind of data flow, and you describe those using C, C++ APIs, and then the compiler will map those into different AI core engines, and then will auto-create the plumbing in between by instantiating or configuring the interconnects and DMAs correctly to make sure it streams the way you want. Now, for the AI inference use case, much higher abstraction, right? We don't even want to expose you to that much details. It's really about working at the framework. And for those of you, have tried our 16 nanometer solutions, we already have Xilinx AI platform, which can take a framework and directly target our Alveo cards as well as Zynq cards. So think of the same kind of flow will enable that for the Verso. And automatically you'll partition between AI engine and the programmable logic. And the suite will contain everything you need from pruning, quantization, compilation, runtime libraries, and also optimized IPs. So the real benefit comes with this AI engine and combined with the PL And here's one of the more detailed benchmark using ResNet 50, right? And then comparing against one of the most state-of-the-art GPUs in the data center space, and we're seeing about 3.5x performance boost compared to those. And this is also giving multiple batch as well. So it's running at the batch 4 for the GPUs with the 1.5 milliseconds as a bounding latency, right? And we also have in-house pruning tools that can further optimize the model complexity itself. For example, for ResNet 50, we can get another boost onto those, putting us into the 4.5x. Now, I'm not a big fan of competitive analysis because everybody kind of moved forward, but just to kind of give you an idea, even looking at today's most sophisticated GPUs with the most latest software, we're seeing a huge amount of leap for all the reasons I talked about. So just to summarize, we rebuilt the AI engine together with a massive architecture change in the Verso to have this kind of major performance boost, which I think everybody daily needs, right? For things like AIs and 5Gs. And with this kind of architecture, we think we can make this device much more software programmable. Again, with lots of hardened IOs, a lot of hardened scalar blocks, so you can focus on your algorithms. And then, we're very unique because you can still make this deterministic with all those VLIW and the SIMD. It is a distributed architecture, so you can really create a predictable solution. And it's extremely efficient, up to 8x compute density at the 40% lower power. So you can find more information on the websites, and we actually do have a demo booth there as well at the number 610. Thank you so much for your time, and I'll take any questions.
If you have a question, please step up to the mic.
Thank you for the great talk. One question I had: how many DMA engines to the DDR do you have? Are they? Do you have for each of the engines capability to dump out to DDR, or is it bunched together and you have one DMA engine?
So I believe the answer is each core does have a DMA. Unfortunately, I don't have any more details than that, so that's something we can maybe talk offline. But my understanding is each core does have a DMA, so you can go to non-neighbor AI cores.
Thank you.
If I understand right, that the FPGA internal structure is not abstracted from the user. So when user have a new version or they want to migrate to a new FPGA, how easy to migrate from one version to the other version?
Are you asking about from different Verso family to different Verso family, or?
Well, since the program is written according to your AI structure, right? So it expressly manages the data movement and the processing, if I understand right. Mm-hmm. If that's the case, when I have a new version of the design, some part is not touched, some was just changed. Does that make me have to redo everything from the same FPGA? The other side of the story is when I want to migrate to a new version of the FPGA, a bigger one, for example, does that mean I have to rewrite the whole program?
That's a good question. So I think, especially with the Verso, AI cores will definitely take a different kind of programming model, right? Like VLW, SIMD. So that will naturally not migrate to, say, PL, right? So, we think, if you go from different product within the Verso family, you should be able to migrate very easily. But then if you wrote code for the AI engine and then trying to go back to device without AI engine, that may be a harder port. But overall, we're trying to abstract as much as possible to the higher language. So when we achieve those, you should be able to migrate more. But there will be migration challenges without AI engine.
I just have a question on the benchmark that you showed. So that ResNet was trained at what resolution?
So those are standard ResNet. So I believe 224 by 224. Yeah.
One of the main issues of efficient DNN is to be able to take care of the sparsity, mm-hmm. the multiplication with zeros. Mm-hmm. Are you doing something special in the architecture in order to reduce the amount of multiplication by zeros?
I asking about the DMA engine having the sparsity features or the AI core itself?
No, the nature of DNN system is that you got sparsity.
Oh, sure, yeah.
Right. The question whether you are doing something special in the architecture to reduce the amount of multiplication by zeros that you would need to do because of the sparsity.
Right. So there are two answers to that. So the programmable logic, absolutely yes. Right. So we, because it's fully programmable, we have different engines that can do a sparse. And in fact, we have a speech recognition LSTM cores that exploits the sparsity and has that. For AI engine part itself, actually, I'm not actually prepared to answer that today. So
Thank you.
Okay, any more questions? All right, very good. Thank you, Nick.
Thank you.
Wonderful presentation. Great. Good job.